Rate of change in the integration standard is specifically talking about kinematics. Now, you would have already learnt about this at NCEA Level 2, but as a recap, there are three components to kinematics. They are displacement, velocity, and acceleration. And they are given the symbols S at t, V at t, and A at t. Now we use displacement and velocity and acceleration because they are vector terms as opposed to distance and speed. And what that means is that they have a direction as well, and so you need to care about the signs of your displacement, velocity, or acceleration. Generally speaking, positive direction is up or right, and negative direction is left or down. Now, in terms of how to get from displacement to velocity to acceleration and the reverse, well, it's just going to be differentiation going down the chain and integration going up the chain. And the reason for that is that if we start at displacement, we have S of t, and if we were to differentiate that, we get the derivative of a distance per time, or that gives us a unit of, if displacement started with a unit of, say, meters, then we've got a meters per time, so now we have a meters per second. And if we differentiate that, again, we have the second derivative of that, which is now a meters per second squared as the time is now squared. And that is our acceleration unit. So we've got two questions to look at. Firstly, an object is moving with a velocity of sec squared t. Initially, it is 3 kilometers from point P. How far from point P is the object when t equals pi over 4? So we have a point P. It is 3 kilometers from point P. So let's just say that there is 3. That's where it is. And it's moving with a velocity of sec squared t. So it's moving, say, in that direction. We don't really know what direction it is. Doesn't really matter. And that's 3. At t equals 0. So how far from P is the object when t equals pi over 4? So we want a displacement because we want distance. So we want to integrate sec squared t. That gives us the displacement equation. Sec squared goes to tan t plus some sort of constant. Now we know that at time is at initially means t equals 0. The displacement is 3. So that will be 3 equals tan 0 plus c. Well, that gives you c equals 3. And so our equation for displacement is tan t plus 3. Finally, how far is it when t equals pi over 4? So sub in pi over 4 for t. And you get 4, and the unit is kilometers. Number 2, water is falling with an acceleration of 10 meters per second squared. When it first goes over the edge, its velocity is 2 meters per second. The water takes 1.6 seconds to fall to the ground. How far does the water fall? So I would say a picture would be really useful for this. Now I'm going to define my axes, and it's really important to define your axes. There, and I've got water falling, it's running down, it's a river, and then it falls over the waterfall. And it goes down, then it hits, splashes a bit. Now, what's going on? Well, its acceleration is going at 10 meters per second squared. That's due to gravity. Now it is going down, which means its acceleration is going downwards, and so our AT equation is negative 10 due to its downward direction. We want how far, so we want displacement, which means we need to go through velocity and then displacement. So velocity, well, that's just the integral of acceleration, so that we negative 10t plus c. Now, to find c, we need to substitute a point. We're told when it first goes over its edge, its velocity is 2 meters per second. So just when it's going over the edge, so it's there, it's going at 2 meters per second. Now, it is actually going downwards, so that means that when t equals 0, its velocity is negative 2. And so we've got negative 2 equals negative 10 times 0 plus c. That means that c is equal to negative 2. So we have our velocity equation of negative 10t minus 2. Now, in terms of your signs for your accelerations and your velocities, it's not strictly crucial to be using negatives here, but as long as you're consistent. So as long as in one direction you stay consistent, if I'm using negative, I use negative. If I use positive, I use positive. Then your answer will be fine. Now I want displacement. So ST equals negative 10t integrates to negative 5t squared minus 2t plus some constant. Now I'm not going to use c because c is already defined as negative 2. I'm just going to use the next letter in the alphabet, d. We're told that water takes 1.6 seconds to fall to the ground. So what that means is, because I've defined s equals 0 at the bottom, that when s equals 0, t will equal 1.6. Substitute that in. 0 equals negative 5 times 1.6 squared minus 2 times 1.6 plus d. That gives you, if you rearrange for d, d is 16. And so our displacement equation, st, is negative 5t squared minus 2t plus 16. Finally, how far does the water fall? Now, in terms of finding out how far the water falls, well, that will be the distance. That will be the distance from t equals 0 here to when it drops. Now, as we already have defined s equals 0 at the bottom, if I calculate the distance at t equals 0, that will give me the height. So I need to substitute t equals 0 here. Negative 5 times 0 squared minus 2 times 0 plus 16. That gives me an initial height of 16 meters.